Hello, I'm Bill Chow, and over the next 25 minutes or so, we'll talk about deep learning on Jetson AGX Xavier using MATLAB, GPU Coder, and TensorRT. So the application that we're going to show all this in is a defective product detection application, and that's running on the Jetson AGX Xavier, as you can see here. So we've got that plugged up, and here is the output of the Jetson Xavier, the display output. And here you can see obviously it's running Linux. And so we built the application, and we're just going to run the executable at this point. And in a second, you'll see here. So what we're doing here is we're taking the input video with all these different hex screws, and we're going to find the hex screws. And we're going to tell you if it's defective or not. So obviously, if it's NG, that means it's not a go, so it's defective. The application deep learning network has seen something, and if it's okay, then this product is fine. So that's kind of the end result that we'll see towards the end of this presentation. And so obviously we have some sort of input, video feeds or videos or images of these different products, and we want to eventually identify whether the different products, these hex screws, are defective or not. So how do we get from the input to the output? So one of the first things we have to do is we have to do some image acquisition. We'll have to pre-process the images to identify the different objects that are in the images. Then we'll send it to the trained network, which will tell us the probabilities of these two objects being defective or not. And finally, we'll do some post-processing to draw bounding boxes around the object and also give you some labels. So once we've gone through and we've implemented this entire process, then we can go ahead, compile the entire application. So this includes the pre-processing, the post-processing, as well as any sort of deep learning networks that you have in the middle. And we can compile that down into the Jetson board. And of course, in order for us to get to the trained network, we'll need to do some collect some training data. We'll need to do some pre-processing before we can go through and train the network. So this is kind of the entire workflow that we'll be talking about. And over the next couple of slides, we'll walk through each of these different steps. So starting with the collection of training data, there are a couple of different ways that we can bring these different sorts of training data into MATLAB. So through your Jetson board and using ROS, we can bring these images into MATLAB. So that's one of the first ways you can work with that. Of course, you can use image acquisition toolbox to connect the camera directly to the host computer where MATLAB is running. So you can bring all these different images and videos into MATLAB. And of course, if you have some videos that were already captured, then you can bring all these different file formats into MATLAB from all these recorded data. So these are some of the different ways you can bring these sorts of training data into MATLAB. And within MATLAB, obviously, there are many different algorithms that is available for you in order to explore different sorts of pre-processing. So in addition to the command line functions that many of you are familiar with, we also provide several interactive applications for you to try different sorts of things. So in this example, we use the color thresholder app, for example, to remove the red background from the input images. And from there, we can run the image region analyzer app to help us to identify the two different hex screws and their locations in the image. And in addition to all these interactive tools, I mentioned all the different functions that you can run. So here are a couple of different examples. For example, we can run image IM adjust in order to adjust the image intensity. From there, we can run region props to binarize these grayscale images and measure the properties of the image regions. And from there, we can use BW prop filter, for example, and IM crop in order to extract the two different objects from this image using the properties we found in the previous step. So we can, at the end, really arrive at two sets of images. So in order to work with the deep learning network, we have to prepare our input images, right? So in this particular case, we started out with proposed regions of those two objects that we were just talking about. From there, we can turn the RGB images into grayscale, as well as to resize the image files into a format that is acceptable by the deep learning network for the next step. So once we run through these two steps, we really would arrive at two sets of images. So the first set being images of the hex screws that are fine, and the second set images of the hex screws that are defective in some way. Now, when you train deep learning networks, in order to avoid overtraining the deep learning network, we have to run different sorts of image augmentation. So using a function called augmented image data store, we can run and apply different sorts of image augmentation. We can apply rotations, we can apply reflections, and we can apply all of these randomly so that it helps us to avoid overfitting the deep learning network. So with these two sets of images, we can look at some of the supported deep learning networks that are available in MATLAB. So broadly speaking, there's kind of these three different types of networks. First type is object classification networks. So these are your convolutional neural networks, which takes a look at an image that's passed in, and it gives you different probabilities of the types of objects that are in the image. Second step is object detection, so somewhat similar to object classification. It also would, in addition to telling you different types of objects that are in the image, it would also identify the different types of objects and tell you the locations of those. So in this particular image, they're identified a car as well as a stop sign. And finally, a third type is semantic segmentation. So at a pixel level, it can tell you what that object or what that pixel represents in terms of objects. So here it can identify the green parts of the road. The blue are pixels that represent different types of vehicles. We can go through and identify the trees, the sky, different buildings, and things of that nature. So broadly speaking, there are these three types of deep learning networks that MATLAB supports. So in our particular example, once we've identified these two objects, then we have to do some resizing before fitting in with the deep learning network. So all this, pre-processing, it's integrated with the classification with the deep learning network. So in terms of designing these different deep learning networks, if we look at the architecture of it, you can start from scratch. If you have a new idea where others really haven't worked with before, you can implement all these different deep learning networks in the precise way that you want to represent it. From there, you can go through, use local resources on your host computer, or pull in compute resources in the clustering clouds if you have access to these. For example, using Amazon EC2, you can go ahead and train your deep learning network so that you arrive at a trained model towards the end. So you can do that from scratch. But there are many research networks that's out there and available for different people to use. So another way to work with deep learning networks in MATLAB is to import these. So if you have networks that are implemented in Caffe or Keras TensorFlow, you can use the model importer capability in MATLAB and suck that into MATLAB. And you can use it as is, as a trained model, or you can start modifying it and do further training. Of course, we also support the ONNX file format. So any network that is represented in the ONNX file format, you can import it again into MATLAB as a trained model or do some further modifications. And also MATLAB supports exporting networks that you develop in MATLAB through the ONNX file format. So in terms of some of the pre-trained networks that's supported natively in MATLAB, we've implemented all of these for you so you can get started right away. Here's a list of that. Everything from BGG to GooglyNet to ResNet, SqueezeNet, and others. Now I talked a little bit about working with pre-trained networks and bringing that into MATLAB. What a lot of people do at that point is they use a process called transfer learning. So they'll bring in a pre-trained network, a network that somebody has already worked with, but then they'll make further modifications to suit their particular needs. So what does that look like? I'll show you a couple lines of code to get you started. So Right at the beginning, we support these pre-trained networks. So with one line of code, you can bring AlexNet, for example, into MATLAB. Now suppose what I want to do is I want to remove the last three layers and put in some of my own. So with one line of code, you can remove the last three lines, and you can add a couple of lines of code: fully connected layer, a softmax layer, and a classification layer. So with just a few lines of code, you can start modifying and adjusting the network to suit your needs. Now you can do all sorts of things with your network, but not all of it is going to be valid, right? So we provide tools, for example, analyze network, to make sure that the modifications you've made still make sense and it's still valid when you run the deep learning network. So once you've done the pre-processing, you've set up the network architecture, you're ready for training. And to train the deep learning networks, again, you can use your local compute resources on your host machine. So the CPUs and GPUs. You can connect to clusters or the cloud if you have access to compute resources, for example, in Amazon EC2. MATLAB also helps you do that very quickly with just a couple lines of code. And with the training process, there are a couple of different options that's available for you. You can select the different types of solvers, the maximum epochs, the initial learning rates, and things of that nature. So in this particular case, we're running it, and here's an interactive UI for you to see the process. The blue bar at the top, the graph at the top, that's your accuracy curve, and you can see that approaching 100%. The bottom, that's the loss factor, and you can see, again, that's approaching 0. And on the right, there's a whole bunch of additional information it gives you as it goes through the training process. So in this particular case for our network, it took about 12 and a half minutes for us to train our deep learning network. And in this case, we were using a Titan XP GPU. And so MATLAB provides a bunch of these different options as well as visualization tools to help you to see the training process. And speaking of visualizations, you can also visualize different features in the deep learning network. So in this case, here we're showing class activation mapping. With a couple of lines of code, you can get that to work very quickly. So here you can see the captured image, and you can start to see with this one here is a defective hex screw, and you can see the plot on the left side where it's red and yellow. That's where the deep learning network is spending a lot of its time, and so it's kind of identified the scratches at the kind of the surface of the hex screw. So using class activation mapping, you can kind of see a little bit deeper as to what the deep learning network is focusing on, and it can kind of help you to better understand what your deep learning network is doing. So once you've gone through, you've implemented the pre-processing, you've got your deep learning, your trained deep learning network going, you've done all your post-processing. At this point, you can go ahead and look at deploying this. So using, for example, GPU Coder, you can generate CUDA code that can then run on any modern NVIDIA processor. So it could be your host machine if you have an NVIDIA GPU. It could be somewhere on the cloud and clusters, or in this case, we're looking at an embedded Jetson AGX Xavier. So with GPU Coder, you have two options. You can use the cuDNN library, or better yet, you can take a look at integrating it with TensorRT, which will give you even more optimized performance running on the Jetson board. So here's kind of the final part of that. Here's a video of that. And what we're going to show here is this is MATLAB, and we've already implemented everything. And this is the final step where we're going to generate the code. We'll compile it down to the Jetson board, and then we'll log in and take a look. So with a couple lines of code, we're going to connect to our Jetson AGX Xavier. GPU Coder will check to make sure that all the CUDA versions, the board, and everything else is working correctly, and we are connected. From there, it generated code. It called the NVIDIA compiler to compile everything into a binary. And here I'm opening a terminal, and I'm going to use SSH over to log into the Jetson AGX Xavier. From there, we'll change directories. Here is the ELF file that we're going to run. In a moment, we'll see a pop-up. And again, in this case, we're using an input video to test our things. And here you can see, our final application, which is able to identify whether the hex screws we're placing on the image is defective or not. So we're running a pretty good frame rate, anywhere between 45 to 55 frames per second or so. And so we, with GPU Coder, you can target different sorts of boards. Here, with the AGX Xavier, we saw anywhere between 45 to 55 frames per second. We also compiled it down into the exact same application to the TX2, and that what we saw was, it was roughly, half of what we saw in the AGX Xavier. So that was a quick overview of the workflow. Now I'm just going to spend a little bit of time to take a closer look at GPU Coder. So GPU Coder, of course, it helps you to generate optimized CUDA code from MATLAB. You can use this for deep learning applications, embedded vision, as well as autonomous systems. So the generated code, you can specify it to be just plain source code, or you can ask it to compile it into a static or dynamic library using the NVIDIA compilers. Now, what's important to note is that the generated CUDA code, it's portable across NVIDIA GPUs. So if you compile it as source code or libraries, you can actually take it, you can run it on your host GPU, you can run it on clusters, you can run it in Amazon EC2 in the cloud, or other cloud providers, and you can even run it on your embedded GPUs, on the Jetson boards or the Drive platforms. Now the generated code, it calls into optimized CUDA libraries, for example, cuDNN, cuSolver, cuBLAS, TensorRT, cuFFT as well. And you can also incorporate, if you already have your existing handwritten CUDA code, you can incorporate all of that together with just a couple lines of code. And obviously you can run all this on different sorts of hardware platforms. In terms of the functions it supports, GPU Coder supports generating code from core math libraries, matrix multiply, linear algebra, FFTs, to image processing and computer vision functions. Here you can see a brief list of that, as well as deep learning networks from Deep Learning Toolbox. So over 300 of these functions are supported. So how does GPU Coder go about compiling MATLAB code into CUDA code? So I'm going to show a quick example of how it does that. So suppose you have a quick line of MATLAB code, which is what you see here on the screen, and you can assume the sizes of the different variables listed as well. So one of the first things that GPU Coder can do is it can apply scalarization. So it turns that one line of vectorized code into two for loops, right? And from there, what we can do is we can apply loop fusion. So we can basically combine these two for loops into one. And with GPUs, the larger kind of for loops or these type of operations, these parallel loops, the more efficient they are. So we want to combine as many large, loops together. And now, if you look at the variable diff in here, you'll see that that's actually a matrix. And for our particular operation, for each iteration of the for loop, we actually don't need that large matrix. Instead, we can turn that into a scalar. So we can apply scalar replacement, and that will turn that into just a regular scalar variable so that we can optimize more for memory usage as well. So these are some of the optimizations that GPU Coder goes through in order to compile it down into CUDA kernels. So this is kind of one half of the process, right? Where you take pieces of your MATLAB code and we try to create these large CUDA kernels, and the larger the better. But that's one half of it, because the other half is we have to consider data movement. So when you're working with GPUs, data is going to reside on your CPU initially, usually, and you have to move the data from CPU memory over to GPU memory. Now, if you do too many of these data copies, that's going to kill performance. So optimizing for CPU GPU data movement is really a challenge and quite important. So how does GPU Coder deal with that? To illustrate this, let's take a look at this piece of pseudocode, and here you can see the for loop as well as the IM filter. So GPU Coder will turn the for loop into one kernel, kernel 1, and then IM filter will turn that into another kernel. Now, how would you how would you move data between the CPU and GPU? If we were kind of, applying a very naive placement of data copies, what you can see here is that before kernel 1 is launched, we'll copy the data from CPU over to GPU, and once the kernel is done computing, we'll copy the data from GPU memory back into CPU, and then we'll kind of do the same thing again for the IM filter kernel as well. Now, when GPU coder takes a look at this piece of code, it's going to understand the data dependencies between different kernels that it's generating. And so, if GPU coder understands that and it figures out this variable that kernel 1 is using, that's actually not touched at all before the next kernel is launched. In that case, we don't have to move the data back prematurely, and we can eliminate some of the data copies. And so GPU coder will be able to do this sort of analysis before it or as it goes through and compiles this piece of MATLAB code. So to illustrate that, I'll show you another piece of pseudocode. So here you can see a couple of variables A, C, and B, and we're going to assume that GA, GB, and GC are really the same variables but mapped to GPU memory. So in the first instance of running this for loop, we'll definitely need to copy the different variable A into from CPU memory over to GPU memory, right? For that first iteration of the for loop. But on subsequent iterations, we may not need to. In subsequent iterations, we definitely know that a CUDA memcopy will not be needed because the variable is already, we copied it once already, so we don't need to make that data copy once more. Now, once we finish the for loop, we may need to copy GC back into C, right, from GPU memory back to CPU memory. And how do we check for that? If that some condition inside the for loop, if that was executed and kernel 3 was executed, then we would need to copy it back. If that some condition was never invoked, then we would not need to make that copy. So the way, if you take a look at this, this is actually equivalent to partial redundancy elimination, which is a well-known problem in compilers. And the way to attack this is to apply a dynamic strategy where we can use status variables to see if we need to make a data copy or not. And so in the generated code, you'll see these different flags. For example, A underscore is dirty on CPU. We'll set that to true. And inside the for loop, we'll check for these different status flags to see if we need to make a memory copy by invoking the CUDA memcopy function. So that's how GPU coder deals with this type of optimization. So having talked about that, the last part is just wanted to mention very quickly the ability to very easily retarget between different platforms. So GPU coder provides you all the configurations for you to deploy, for example, the NVIDIA Drive platform or even the NVIDIA Jetson platforms. Everything from TK1s through the latest AGX Xavier. So for you to quickly change between them, all you need to do really is that at the build type, you need to set that to a library, and in the hardware board device part, you need to set it to either Jetson or NVIDIA Drive or NVIDIA Jetson, and that's will help you to very quickly retarget this exact same application to different Jetson boards. So here's an example. Again, this is an example of something running actually on the NVIDIA Drive platform. Here's a semantic segmentation that's running. And here you can see that very large board in the middle. That's the NVIDIA Drive PX2 board. So wrapping up, what we talked about is kind of this process where you start with image acquisition, you do data processing or pre-processing, and you run that through the training network before you do some post-processing. And all of this complete application, the deep learning network, the trained deep learning network, any pre-processing, post-processing that you have with it, you can use GPU coder to compile that down into CUDA code, and you can integrate that with TensorRT for optimum performance. Thank you very much.